Hello. Well, here we have most of the frames. There's a few um, over on the bench there getting deburred, but we have most of the frames, the jacking frames sitting here. The bottoms have all been machined and the side reference has all been machined. And we come to the point where it's time to bore out the hole to put the bronze bushing in. And if you look closely, you can see that the hole is skewed slightly upwards. There's a bit more meat between here and here than there is between here and here. I set them up like that and built a jig so my father-in-law could weld these all together, and he welded it the way I wanted. And then I machined all the bases and all the sides, and then I set up the first one on my boring mill to bore out the hole, and discovered that we'd welded the blocks on upside down. So, not good. One of those awful mistakes that gives you a sick feeling in your stomach. So I called the customer immediately, and we talked about it. This was on Friday. So over the weekend I came up with a few options on how we could possibly save it. We both decided that rebuilding from new wasn't an option. It was just going to cost too much money and take too long. So one of the options I came up with was to move the bore, move the location of the hole by boring it larger than we were originally going to bore it out. You can move the location of a hole by shifting the axis to where you actually want it, and then just boring the hole bigger and bigger until you completely consume the old hole within the new hole. Of course, it only works if the holes are a short distance apart. Otherwise, you end up with such a large hole that you could actually end up boring through the side, the bottom. So anyways, that's what I'm going to do. It results, and then after we do that, I'm going to sleeve the hole with a steel sleeve, and then a bronze bushing is going to go. The original bronze bushing will go inside of that. So in the end, it'll work out fine. Functionally, it'll be just like it was supposed to be. It'll end up being a bit more work for me and a bit more expense, but it's much better than starting over from scratch. can see the results of moving the hole in the very first frame. This is the first one. I was doing some experimenting. The end result is that the hole ends up being half an inch, a little over half an inch in diameter, bigger than originally intended. Originally this was supposed to be bored out to 3 1/4, and then the bronze bushing pressed in, and now this is just under 3 7/8, and that allowed me to completely consume the original hole and move the axis down to where it's supposed to be. This is the boring bar I'm using. I made this last week. It bolts directly to the milling spindle, which is the more rigid of the two spindles in a boring mill, and it's a solid bar with the adjustment at the outer end. I've been doing a lot of reading on Practical Machinist lately about this type of work, the best way to bore holes on a boring mill, and the guys that actually do it consistently say don't use a boring head, get a solid bar and put the adjustment at the outer end of the bar. And it makes sense because a boring bar is essentially a cantilevered beam, and on all cantilevered beams, when you have a load out here and it's restrained back here, the maximum force applied to a cantilevered beam always occurs where the beam attaches to the structure. When you have a boring head back here with a bar sticking out of it, the weak spot, which is the slideways, end up being put right in the highest load position, and you end up with a better result if you put those out at the end where the lowest load condition occurs. You can see this in the design of the Devlig micro bore bars, I believe they're called. They made a line of bars, I think other people have since copied them, where they mount, and it's just a solid bar right up to the end, and then there's a cartridge that you adjust. And I've never used one, but anybody who has swears that they're about the best way to go because they're so rigid. I have to say I completely agree now, having bored this out. It took me a long time to bore this out because I started out with light cuts and light feed rates, etc., because I wasn't sure how this would handle it. And in the end, I started, I was opening up the bore about 200 thou a pass. It's taking 100 thou deep cut, and it was handling it no problem at all, and getting good insert life, and yeah, it's worked out really well. So the next one that I do, now that I know what I'm doing and how to actually open this hole up and move it downwards, it should go a lot faster than this first one. I thought I'd show some of the results I got of the boring. I'm having a bit of an issue with this boring mill when I face stuff square. I'm getting about 5 thou lean and 9 inches, 8 to 9 inches that way, as though the column is tilted towards the table. Yet when I put my known good square on the table and run the headstock up and down with the dial indicator attached to it, I'm getting like 8/10 and 20 inches. I haven't been able to figure it out why it's like that. But boring this, boring these two holes in the same setup to the same diameter, is another test of squareness, you could say, at least in this case, between the spindle axis and the tabletop. So I took my indicator and swept to find the bottom of the hole, and I took that end as 0, and this end is down 1 thou and 2/10, and that's over a distance of 8 inches. So considerably better than the roughly 5 thou out of square I'm getting in that distance. So really doesn't shed any light on anything. I'm still in the dark as to why that's happening. But one thing that I'm quite happy with is, you know, in theory, both those holes should be exactly the same size. And the reason behind that is I'm boring with a bar of constant length, and I'm feeding with the saddle. I'm feeding with the table, essentially. Therefore, the effective length of the bar remains unchanged during the whole travel through the two bores. Therefore, in theory, they should cut to exactly the same diameter. Often the theory doesn't work out. Often reality doesn't match theory. However, in this case, I'm happy to say that it's about as close as you can get. Those are the dimensions there, 3.8193, that I measured at each end using a telescoping gauge and a tense micrometer. Then I got a dial bore gauge and tested it, and it bears out what the telescoping gauge is saying. I'm getting, if you look here, I get a little needle jump. This is a tense gauge. I'm getting a little bit of needle jump just because of the surface finish, I think, is the cause of it. Pull that back closer to the outer edge. But you can see it's pretty much right on zero. Maybe within a tenth or so. Spin this around. We'll do this end. And we'll do it right near the end so that we're measuring at the two extreme ends of travel. And you can see we're getting pretty much the same thing. So it's coming out within over an 8-inch distance. It's boring the holes the same diameter within probably a tenth. And again, it's a little bit hard to tell. This isn't the finish is nice. It feels nice on the fingers, but it's not a ground finish by any means. So there's stylus marks from the feed marks. So it makes a tense gauge bounce around a little bit, and it's hard to get a perfect reading. But I would be confident in saying that those bores at this end and at this end are the same within probably a tenth or a tenth and a half. So I'm very, very happy about that. I don't think anybody can complain about that unless they're building instruments or something. So here's the result of opening the hole up and consuming the old hole in order to move the axis down to the correct height above the bottom of the base plate. We can see the original hole there in that one and the open up hole, and this will then be, the idea was we would sleeve this down and make the bore of that sleeve 3 1/4 inches, which will fit the bronze sleeve that has to get installed in there. However, we ran into a problem. Not all the flame cut holes were in the same location. They're out enough that I think possibly it wasn't me machining these sides relative to the, I didn't do them relative to the hole. I just machined 1/4 inch off all the way around. But the difference in hole position is enough that there's no way that the difference in hole position was caused by me machining those sides. So I think when they were cut with the torch, flame cut, I don't think they all came out exactly the same. The end result is, rather than being just under 3 7/8 as the diameter to that's required to move the hole, in this one we're 4 1/16, and that's just too big because there's a series of 4 bolt holes here that have to be put in, and they're essentially breaking through here. So I came up with another way to repair these, and we're gonna try it and just see. It involves some welding, so we're gonna just do one as a trial because we're a little bit concerned that the welding may warp the base plate We think it probably won't, but we're just gonna do one first just to see. But anyways, what we'll do is, the idea is I'll come in and just clean the original hole up just to get rid of the mill scale. And that's about 2 3/4 inches in diameter. And then I will just, maintaining that diameter in the boring head, I will drop the spindle about 100 thou at a time and machine this down until I get to the correct center line. So I'll essentially make a bit of a slot with rounded ends. And then when I get to that center line, I will keep making passes through without changing the center line height, but I'll increase the diameter that the boring head is cutting until I get this out to about 3 1/8. And at that point, we will have, we're at 3 1/8, and we'll have an open spot up here that we will then fill with weld. And then I will go and I will bore that hole that's 3 1/8. I'll bore it out to 3 1/4, and we won't put a sleeve in. We'll bore it right to size to fit the bronze bushing. I have two concerns about this repair, and that's why we're just doing one to try it. Possible warping of the base, and secondly, fact that part of the hole is going to have a weld in it and part of it's going to be parent material. And I know from experience that the weld will be a bit harder than the parent material, and I just don't know how that's going to affect the roundness of the hole, or whether it really matters if the hole is almost round and we press the bushing in and the bushing deforms slightly. I was planning on having to slightly bore out the bushing anyways, because it's going to crush down and probably pinch the shaft that passes through it. So it's just one of those things that you can't, it's hard to predict what's going to happen. You just have to try it and then see. So I've pre-machined one. I got it finished last night, and my father-in-law is coming in this morning to weld it up for me. And you can kind of see there, now this is upside down compared to the one I was just showing you. But this is the hole this is the part that's now at 3 1/8. This is actually still at 2 3/4 or close to it. And we will fill this with weld. It'll be just about a 1/2 inch thick down at the base and taper off. And we want it so that essentially it cleans up when I come in at 3 1/8, and then I will open it up an extra 1/8 out to 3 1/4, and then everything should clean up. We're gonna try this because our sleeve repair isn't gonna work with the ones that have moved, that are way out of position. The hole just gets too big. And if this works and it doesn't distort, we'll do all of them like this. The remainder of them. I've so far only bored out 4 for the sleeve repair when I hit the one that got really bad. So we'll give this a try. And I've taken this one and put it on my, I got a small granite surface plate, and I just tried to get under it all around with a 1 thou feeler, and I couldn't. So I'm gonna call this flat better than a thou right now. After welding, when it cools down to room temperature, that's the first test. We'll see if it's still flat. And if it is, we'll proceed with boring. So we have some results from the new repair where we're just welding on the top half. I've actually got the 4 stages of repairs sitting here from left to right. Our test subject worked well. This is it here. And after welding, I checked, and it was, the flatness was just under 3 thou, which is acceptable. And the boring went well. But I'll just show the 4 steps. So, well, first one's not a step. The first one's a mistake. And you know, the hole needs to be shifted down. This is after pre-machining to move the hole axis down. We have the 3 1/8 diameter here. This is the 2 3/4 diameter. This is after welding. And then this is after machining. And I'm not sure if I'll be able to show the finish there, but it came out quite well. And I measured it, and it seems to be very round. The fact that the weld was slightly harder than the parent didn't seem to have much of an effect, or at least not enough to be a concern. So the repair is it seems to be good. So we're gonna continue on with that. And I've bored out all the frames now. And the original 4 that we bored out way oversized for the sleeve, we decided to weld those up too. Now those ones distorted a little bit more. I'm getting about a 15 thou of distortion on the base plate. So I'm gonna leave those ones till the end, and what I'll do is I'll just take a light facing cut on the bottom again on those ones and get them flat, and then I'll bore the hole out to the correct size. So they'll be functionally equivalent to the other ones. So yeah, the repair is sound. I'm just getting set up now to start doing the finish boring on the welded. I just finished doing this step. We ran into one other problem though during this repair, and that was my boring bar setup. I was earlier in the video you saw me using this setup, and it was working good for a while. And this tool I got actually worked quite well. I wasn't sure when I ordered it if it was going to be very good or if it was kind of gimmicky, but it's actually quite well made. It's very rigid, and that part worked out well. And I was working the shit out of this too. It turned out I was taking 200 thou depth of cut with this setup. I was under the impression I was taking 100 thou deep cut, but for part of the circle I was actually going 200 thou. I had opened the bar up, opened the head up 100 thou on radius, which gives me 100 thou depth of cut. But then I also dropped the head 100 thou to move the hole. So at least on the bottom part of the hole as it was cutting, it was actually taking a 200 thou cut. And that's shown earlier in this video. At the time I filmed it, I thought I was taking a 100 thou cut. So yeah, this part held up well. Part that didn't hold up so well was the head itself. And I can't see any actual signs of damage, but I think I'm distorting it. I think the cuts I'm taking are so heavy that this thing's distorting, because it's gotten to the point where I can hardly turn the screw with the long end of the Allen key. It's gotten so stiff, and I managed to get it apart, and I cleaned everything and put it back together, and it seemed to be a bit better. But I bored out one frame, and now it's so bloody hard to move that it's almost useless. So I thought, well, I got a lot of these to do, and I can't be buggering around with this all the time. So I came up with something different, and I just made a really basic boring head. It screws onto here. If I was doing this from scratch again, I would probably just make this all one bar, but I had to put a 1.5 18 thread here to screw that boring head on originally. So I just did the same thing. I cut a female 1.5 18 thread in this boring head, I'll call it, and then I just put a 3/4 inch cross hole to hold the tool. I put a 1/2 inch hole to hold the dial indicator, and then I just put obviously the clamp screws in, and then I had to make this tool to hold the insert, and I decided to switch to from a CCMT insert to an SCMT insert, or a square one, mostly because the square ones have 4 usable edges, which is nice. Instead of 2, you get twice as much machining out of your insert. And for this type of work, I'm not trying to machine a shoulder, so not having a lead angle of 0, not being 0 is okay. In this case, my lead angle is 15 degrees, and this has worked very well. This insert, it's a Sandvik insert. I'm on my second corner, and it turns out I could have done these all with one corner. I indexed it once thinking I was having a problem with the insert, but it was something else. I'm pretty sure I could have done all 22 frames with jacking frames with one corner of this insert. It's I think this one's done about 9 frames, and other than discoloration, there's not really any focus. There's not really any wear on the edge. So this has actually turned out to be to work pretty well, at least for roughing. You know, at caliper accuracies, I'm hitting size within 1 thou or so, and when I go to do my finish sizes, I'll just have to be a bit more careful. Currently, what I'm using is this setup. I'll just put it in. It's pretty obvious how it works, but this is much easier when you got an extra hand. And then just set it in, and obviously lock it in, and then I can loosen the 2 screws up and then just move it. Now I bought this end for my indicator, so I have a flat surface, and you can see that it doesn't really line up with the tip, and the reason for that is my original version of that bar, I made this with a 45-degree lead angle, because I'd had pretty good, obviously that sat here, and when it sat there, it lined up perfectly with the indicator. Now I've had really good luck with 45-degree lead angle tools in the past, both carbide and high-speed steel. So I thought, yeah, that's the way to go. And of course, the way machining is, something that works perfectly fine in one circumstance is completely useless in another. And that's what happened. When I tried using this, I had all kinds of vibration. And so I did a little bit of looking around. I was on Sandvik's catalog, and their bars that use the SCMT, they always have a 15-degree lead angle. So I made another tool with a 15-degree lead angle, and it was night and day. It plows through the material really well with barely any any sound, barely any vibration. So this setup works really good. Before I do my really fine work, I'm probably going to make a new bracket and just move this over so I can actually touch the edge. So far, however, it seems to work pretty good just the way it is, but I'll extend this over anyways. And I'll keep this bracket in case I end up using this tool in the future. But the nice thing about this, it's obviously very strong and robust. It's just a big slug of metal with a hole in it. There's no dovetails or adjustable gibs or anything. So this has turned out to work quite well. So, and it's actually become surprisingly easy to adjust once you do it a few times. Other thing, which is a minor detail, but this is something that pissed me off about that small boring head. To make adjustments on that small boring head, you needed 3 different Allen keys, 2 of them metric, 1 of them imperial, which I thought was just ridiculous. So one of the criteria I set for myself when I was building this is I want to do everything with a single Allen key. And it turns out that 5/16 set screws and 10/24 cap screws use the same 5/32 Allen key. So I'm able to do absolutely everything that this boring head can do with 1 Allen key. So it makes it easy to adjust and easy to use. And it's very robust, so I'm pretty happy with the setup.